to this October NORR for 2024. This year, we address the future of architecture and engineering, as you can see with this year's guest speakers. As founder and host 18 years ago of NORR, my objective was to meet three main goals: teach, learn, improve, and to do that continuously. The program relies on the best guest speakers in three series: architecture, engineering, and masters. Each of the NORR virtual sessions since 2020 have been recorded and are available on NORR YouTube for global access. This session is being recorded and will be posted in a few weeks. Our guests are invited at no cost through our 14 global offices. We are proud to include 16 schools of architecture in our invited program. Our engineering series today is on fire protection engineering, a design discipline that has become extremely complex in the global affordable housing crisis and associated global warming crisis, both of which have developed over the past decade. A design discipline that is not just about codes and regulations, but about protection and commitment to the public good. We as architects and engineers, professional acts worldwide, mandate that we as a profession adhere to four professional principles, including 1, expertise; 2, autonomy; 3, the commitment to public good; and 4, accountability. The global built environment has been changing so rapidly and influenced by multiple outside factors that the protection of the public good has been eroded. One devastating example of this is the Grenfell Tower. On the 14th of June, 2017, a high-rise fire broke out in the 24-story Grenfell Tower in North Kensington, West London. Recently, on the 4th of September, 2024, the Inquiry published their final report. The report forms a devastating verdict of incompetence, dishonesty, and greed that caused a disaster in which 72 people died. The 1,700-page report chronicles failures in the construction industry, regulators, and the central government. Where was professionalism, and where were the professionals? How much is one life worth? How much are 72 lives worth? Grenfell is not the first and will not be the last. The 1,700-page report documents the crisis in the protection of the public good. Is this sustainable? Susan Lamont has worked in fire protection industry for over 20 years in the UK, the USA, the Middle East, Asia, and Africa. She is a character engineer and Arab fellow of the Society of Fire Protection Engineers, and a member of the Board of Trustees for the Fire Protection Research Foundation of NFPA. Susan brings local knowledge and international fire safety experience to a diverse range of projects for Arab clients around the globe. Her specialist experience is in the performance of structures and materials in fire, and in particular, resilience of buildings or infrastructure to fire. She has worked through all stages of design and construction on a diverse range of projects, from large assembly buildings, hospitals, schools, shopping malls, and offices to master plans and transport hubs. Her role is to guide the developer owner through fire safety design, testing, and commissioning to occupation, and wherever possible, to fire safety management of the component buildings. She works closely with her clients and the local authorities to maintain a high level of fire safety in new and existing buildings. Recent projects include the Abu Dhabi International Airport Midfield Terminal Building and the Guggenheim Museum in Abu Dhabi. Susan is also heavily involved in the development of codes, standards, and industry guidelines. She led the development of the Dubai Building Code published in 2021. As one of Arup's fellows, Susan works closely with Arup University to raise standards across our industry on issues spanning health and safety, technical achievements, sustainability, and social value. She's here today to speak to us on this presentation of NORR on fire protection, shaping a sustainable future. Welcome, Dr. Susan Lamont.
Thank you, Silvio, for inviting me today and for the wonderful introduction. It's an absolute pleasure to be here. So I want to share with you today that our global fire engineering team are celebrating 50 years this year, and we're looking back at our origins, celebrating our teams, and looking at our impact and trying to foresee and plan for the fire safety challenges and opportunities of a sustainable future. Just for some context, we started with one fire safety consultant in 1974, and we're now over 300 consultants across 18 countries. But what is a fire safety engineer? Many of you in North America will be more familiar with the term fire protection engineer, and Silvia's already mentioned that term, or fire safety code consultants. Our founder, who was an eminent fire safety scientist called Margaret Law, defined fire safety in the terms shown here on the slide. They need to have a basic engineering, a knowledge of assumptions and understandings of the assumptions. We need to be able to understand, measure, and quantify the fire phenomenon. We need to understand that no one person could hope to be an expert across all the aspects of fire safety. And most importantly, she said we had to have an intellectual toughness to deal with matters in a rigorous, analytical, and honest way. While I agree with all these definitions, it's much more than this. Ultimately, a fire safety consultant develops holistic fire strategies to enable design teams, contractors, and owners to design, build, and operate fire-safe buildings and communities for the people that live and work there. In this role, we identify gaps in knowledge, and we try to fill them through research. We influence codes and standards writing, we collaborate with others, and we act as expert witnesses and much more. And I hope to tell you some more of that today. We have grown from our origins as fire scientists to become researchers, engineers, experts, advocates, and increasingly enablers of sustainable solutions. The breadth of work we do and the impact we have has grown exponentially over the last 50 years, with the last decade being extremely fast-moving, shocking, and really humbling in equal measure. I want to talk to you today about where we have come from, what we have achieved, where we have struggled, and how we are dealing with the current fire safety hazards, and what we are doing to prepare for the challenges of a sustainable future. You will see that each decade of the last 50 years is characterized by a significant shift in how we have evolved to become the fire safety consultants that we are today. And I'm going to try and focus on a shift per decade as I go through the presentation. So if we start in the beginning, back in the 70s and 80s, and I wasn't around at that time, but the fire engineering practice was. In 1974, Margaret Law moved from our research and development team to create our fire safety engineering practice. She was really a fire safety scientist at heart, and she was asked to start fire engineering at Arup because there was a demand from architects to be able to design without the constraints of the prescriptive code requirements. Famous architects like Renzo Piano, Richard Rogers, and Norman Foster wanted to have exposed structural steel, large open plan spaces, and interconnected floors, all of which were not possible under the codes of the day. Margaret brought her knowledge of fire safety science into the built environment and developed calculations and methods of working to allow many of these buildings that we're now famous for. The iconic unprotected external steel structure of the Pompidou Centre was made possible because she had a really deep understanding of compartment fire dynamics and heat transfer to that external steel diagrid. She developed a methodology from first principles to calculate the exposure of external steel diagrids to flaming from the windows. The fire science was available, but applying it to building design was unprecedented at the time. Using another approach with the latent heat of water as a heat sink, she worked with our public health teams and material experts to deliver fire resistance via water-filled columns and beams. And she brought this approach to projects like Bush Lane House in London. Margaret also brought fire safety science to means of escape, smoke management, fire spread, and all the components of a robust fire strategy that we're familiar with today. She used fire science to quantify and document the fire safety achieved by her designs, and the Hong Kong and Shanghai Bank is another great example of her work in this space. In the late 1980s, Norman Foster's vision for the new terminal at Stansted Airport was for natural light, exposed structure, and a large open plan concourse. The long travel distances in this space and the lack of fire compartmentation meant it did not comply with the traditional prescriptive fire safety requirements and would not have been possible without fire engineering. Our team realized that most of an airport terminal, if you really look at it on the right-hand side of this image, is really given over to circulation and low fire load, and the fire hazards are primarily in the retail units or the restaurants. Having realized this, they developed what we now call the cabin concept to contain fire and smoke to the retail units and stop it from spreading into the concourses. This approach had two benefits. It allowed occupants to walk away from the fire starting in the retail units to a place of safety outside in the concourse, and it allowed firefighters to come into the building and reach the fire contained within this cabin. And it had the added benefit of allowing the airport to continue operating, or at least for the downtime to be significantly reduced. We've applied this concept to airports and transport hubs all over the world, from Kansai Airport in Japan to Chetlap Airport in Hong Kong. And most recently, we applied it to the Midfield Terminal building in Abu Dhabi. Our fire safety engineers of the 70s and early 80s were bringing fire science into the built environment to enable solutions that met the intent of the codes through performance-based designs before regulations allowed us or provided the route for that approach. As we move into the 1990s and the 2000s, we had a growing portfolio of projects, and fire safety consultants were now based in Hong Kong, Australia, and the US. Performance-based design was regulated as an acceptable approach to fire safety in England and also in Australia. But the focus was changing from bespoke solutions for a particular technical problem to the development of a holistic fire strategy for buildings and infrastructure projects. Our use of computational fluid dynamics and evacuation modeling tools allowed us to design smoke control systems and conduct timed egress analyses for large assembly buildings, such as the Eden project in Cornwall, also exhibition centres, transport hubs, and stadia. But the biggest shift in this decade was in the fire resistance of structural steel and the focus on regular commercial office buildings. The steel industry in the UK and Europe were very focused on increasing their market share in construction. Their biggest challenge was fire safety, as the cost of fire protection, or fireproofing, as you may call it in the US, took time, and it was a major cost factor on site. In 1990, there was a really large, famous fire in a 14-story office building under construction in London. There was little, not in London, in England. There was little or no fireproofing on the structural steel. This fire showed that a composite steel frame structure could survive a fully developed fire without collapse, despite the steel frame being unprotected. So we recognized at this time that fire protection of steel would become a really important topic in the near and medium term. Our structural engineering teams were designing taller and taller structures all over the world, and composite steel construction was becoming really prevalent. So after this fire, the Cardington framed fire tests as they became known, were funded by the steel industry in England. The BRE, or the Building Research Establishment, built an 8-story composite steel frame structure in a large aircraft hangar in England, and they carried out 6 full-scale compartment fire tests across the steel structure. They had lots of thermocouples and strain gauges across the structure to measure the temperatures of the fire, but also to measure the temperatures and the structural behavior of the steel in the concrete slab. The University of Edinburgh at that time secured a grant to research the Cardington frame fire tests and understand why, despite deformed steel beams, as you can see here, and really large deflections of the floor plate of up to about 800 millimeters or 32 inches, the frame did not collapse, it remained standing. The University of Edinburgh brought together a team of professors, postdocs, PhD students, and third-party stakeholders, including Arup, to deliver this project. Arup funded a PhD in this group, and this is when I joined Arup and I joined this research group. And at the time, I had no idea what I was getting involved in. For the first time, we really realized that the performance of structures in fire was highly nonlinear, not just in terms of material strength and stiffness, but also in terms of how the steel frame performs. We realized that thermal expansion of the steel was the really dominating factor that led to the buckling that you can see in these pictures and to the large deflections. The buckling that you can see in those beams actually happened at about 150 degrees centigrade, which is far lower than we protect for. We assume that steel can reach about 500 degrees centigrade before it really degrades. So the deflections of the floor slab that followed were primarily due to expansion and not a loss of strength and stiffness, and this was really important. In fact, the buckling and the deflections were really good for the structure, as the forces that were generated in the fire were released as thermal strains and movement and not absorbed as stresses or forces on the structure. This research produced validated and verified finite element models for calculating the performance of steel structures in a fire. And the work was easily and immediately applied to design in our Arup offices around the world. The terrible terrorist attacks of 9/11, though, brought several high-rise buildings to the ground, and the forensic investigators needed to understand why the buildings had collapsed. Of particular interest was why World Trade Center 7 had collapsed, because it hadn't been impacted by aircraft, and it collapsed purely because of an uncontrolled fire. There was no firefighters fighting the fire in that building. The expertise to immediately undertake this forensic work and to understand what had happened really only existed in the UK and Europe at the time, and particularly with the University of Edinburgh and our team. NIST reached out to us to understand our work. And much of the published research that we had created arising from those Cardington frame fire tests provided the framework for their investigation and forensic analysis of the actual collapse mechanisms. We also invested further research in structural fire engineering, and it continued at pace. We sponsored further PhD research into our own investigations of the collapse of the World Trade Center towers, including World Trade Center 7, looking both at the fire development and also the fire resistance or structural performance. By 2001, we were able to design structures in response to fire in the same way as structural engineers design for live loads such as wind and seismic. Importantly, we could quantify robustness and really design knowingly rather than relying on the standard fire resistance tests of a single beam or a column. This period of research resulted in a new service for our clients. Unfortunately, many of them became focused on the savings to be made in steel fireproofing or steel fire protection, but the real value was really in an increased knowledge in how structures perform in fire and the ability to increase their resilience in a knowing way. In 2002, we calculated the structural fire performance of Plantation Place in London. We proposed a quantified solution for fire resistance with the added benefit of completely unprotected secondary steel beams. Gaining approval for this project in the City of London was as much about technical expertise as it was about sharing knowledge and building relationships, gaining the trust of the approving authorities. We invested in training sessions for the city and other authorities to explain why this work was so important. And we really emphasized that we were designing the structure for fire exposure in the same way as we do for wind and seismic. And it wasn't about cost savings. And it wasn't about blindly following the tabulated data in the code. Around the same time, our colleagues in China were delivering this amazing building, the brand new CCTV building in Beijing. Many of the authorities in China had been educated alongside us in Edinburgh and were very aware of the structural fire engineering work we'd done. And they asked, why is Arup not doing structural fire engineering on this project? Why are you following the prescriptive code solution? They rightly wanted to understand if the code compliance solution was sufficient for a building, carrying load at these angles. The client appointed us and we were able to show that the design solution was not only code compliant, but achieved the performance that it needed. So these were the first of several structural fire engineering projects using finite element methods to calculate structural response and design in robustness. This next one, Heron Tower, was unique because it had interconnected floors. So every 3 floors formed like mini atriums. And for this building, we designed for not only a single story fire, but a fire spreading through all 3 stories at the same time, using much of the research we developed for World Trade Center 7. So these in structural fire engineering continued with our investment into fire dynamics research for large open plan compartments. The tools we were using were limited to post flashover fires in very small compartments of about 100 square meters or 1,000 square feet, so like a typical hotel room. We knew they were not addressing real fires in large modern open plan offices. And we knew that large compartments, a fire in a large compartment will generally burn in an area until the fuel is gone, and then it will travel to the next package of fuel and burn there. So you get what we call a traveling fire. And this was, evidenced in the World Trade Center fires as well. So again, we funded research, including full-scale fire tests, to develop new theory and fire models to better estimate traveling fires across large open plan offices. This knowledge was then transferred to our work as a new series of design fires. The structural response to these fires was then studied for application to our designs. And this image just shows that large compartment test that we studied. We had full-scale fires in this space, and we were able to capture that traveling fire theory. By the mid-2000s, in parallel to our work in structural fire engineering, we were taking a stance and really advocating strongly for what we call total fire engineering. At this time, fire engineering was treated by many as a vehicle to deliver cost savings and little to do with the fire safety of people or property protection for assets and operations. It was a very difficult time to be a fire engineer, actually, at this time. Total fire engineering to us is about achieving all the fire safety goals of a project in balance with other project objectives and constraints. It is about delivering this through design to operation of the building for the whole life cycle, and it mirrors OVARUP's vision of total architecture. It's important to note that fire safety objectives are not always just about life safety, and they can include continuity of operation and property protection. Constraints may include function, aesthetics, social or environmental considerations, and of course, economic objectives. Importantly, total fire engineering is about supporting the design, construction, and client team to deliver the fire strategy. This is regardless of whether the fire strategy is based on code, so a code consultant is delivering it, or entirely performance-based, delivered through fire engineering, or somewhere in the middle, which is quite often the case. The important point to make here is that the competency required for that is the same. So we had become involved in the construction and commissioning phases of several projects and realized the value of our role in this space as custodians and champions of the fire strategy. We were checking exit paths, making sure fire safety systems operated, witnessed integrated testing, checking fire stopping, etc. We also insisted that the fire safety documentation and fire safety plans be provided for the continued operation of the assets. This diagram shows the breadth of disciplines and people involved in delivering fire safety on a single project. It's important to note that while a fire engineer can provide guidance and be a point of contact, they cannot possibly deliver all of this on their own. And it's really important to remember that everyone in the project team has a role and is responsible for fire safety and design. Dublin Terminal 2 is a really good example of where we had a large team of fire safety engineers present on site for more than a year, helping check that the fire strategy had been delivered. Fire safety of the multi-use high-rise shard building was also delivered through total design, construction and commissioning to hand over an ongoing operation. Phased evacuation, including lift evacuation, was a key issue for this project, as it is for many of our high-rise buildings. And it was really important that the owner and operator understood how the design delivered on that fire strategy so that it operated properly. We still support the landlord and the tenants of the shard today, providing a two-way learning of how fire safety of a building evolves in an operation. So we're able to learn from them and vice versa. Our teams elsewhere were doing the same to deliver amazing projects such as the Morpheus Hotel in Macau. The solution for this 130-meter high atrium is performance-based, considering both evacuation and CFD modeling to design the egress paths and smoke control systems that protect them. By this time, I was living in the Middle East, and I started my 10 years of involvement during the construction phase of the Midfield Terminal building in Abu Dhabi. As part of Total Fire Engineering, our teams were advocating for the careful use of insulation materials in building envelopes. Energy targets set by the building regulations in the UK, Europe, USA, and elsewhere were resulting in the use of highly insulating foams in exterior walls. We were seen by many as preventing sustainable design solutions. Our clients, architects, and facade engineering teams followed our advice, but there was real significant frustration. And this brings us to the 2010s, which were dominated by building envelope fire safety and another significant shift for fire safety consulting. The consequence of industry using lightweight, low-cost aluminium composite panels to clad buildings built during the 1990s and early 2000s was really coming to light all over the world. This was especially true in cities that experienced boom time construction when lots of buildings were all built at the same time. And sitting in the Middle East, we were seeing a significant cladding fire almost every 4 to 6 months. The Address Hotel shown here in Dubai on New Year's Eve in 2015 was probably the most shocking for this region and the most severe, but there was no loss of life. The UAE Fire and Life Safety Code of Practice was updated in a very short space of time to set really stringent rules for exterior walls and to mandate testing and certification for all products and facade systems. This was strictly enforced and third-party inspections were required of the facade system during construction. It's important to note here that when you're working internationally, you must be aware that testing and certification or common practices in your home country may not be common everywhere. So it's important to clearly explain what is needed to the facade team, client, and contractor in this regard. So the UAE had made its code updates and addressed new buildings, but the code was not retrospective. In May 2016, I led a team to deliver workshops with civil defence in the UAE on possible strategies to tackle the thousands of existing buildings with combustible cladding in the UAE. We brought together fire safety engineers, facade consultants, and our advisory team to help explain options for financial delivery of retrofit projects at scale. We explored a city-scale risk-based approach to prioritising retrofit, looking for clusters of affected buildings and their possible impact on critical assets nearby, such as hospitals or power plants. The UAE Civil Defence asked us to host a larger workshop involving civil defence from neighbouring countries and stakeholders such as insurers to gain momentum around this approach. This was in May 2016, and just over a year later, on the 14th of June 2017, 72 people died in a fire in Grenfell Tower in London, and the whole world was really taken aback and shocked. A public inquiry was initiated by the UK government to examine the circumstances around the fire, report its findings, and make recommendations to try to prevent what went wrong from happening again. Dr. Barbara Lane of our team was an expert in the inquiry, supported by a small team of our engineers and consultants. The work of the Grenfell Tower inquiry has resulted in a profound understanding of the systemic issues in the built environment industry, including behaviours and practices that left Grenfell Tower in the condition it was the night of the fire. That condition was such that a fire took place, spread really rapidly and with catastrophic consequences for so many. A fire that has subsequently been deemed entirely preventable. The bereaved, survivors, and residents of Grenfell Tower must suffer on in the wake of this harsh knowledge. This year, as part of our work for the Grenfell Tower inquiry, our fire safety engineers and complex system specialists have developed this change framework. The 6-element change framework provides context and a change narrative for a suite of recommendations made to the Grenfell Tower inquiry. All 6 elements are key to enabling the built environment industry to move towards creating an effective and equitable fire safety system. The framework and recommendations are extracted from Dr. Lane's report to the Grenfell inquiry, Phase 2 Recommendations 23. This provides the detailed analysis underpinning this framework. I'm going to highlight just one element, and I'll focus on the 6th element, which addresses equitable fire safety provisions for vulnerable people. So you'll see that for each element, we describe the current condition, the prevailing practices of that current condition, and then we're asking for a shift to a new condition and the operating principles of that equitable fire safety system or that new condition. So for equitable fire safety provisions for vulnerable people, we're noting that the prevailing practice, we have equality of access, but not equality of emergency egress. The demographics are overlooked or selected as an unreasonable basis when formulating the occupancy profile for the purposes of design and formulating fire safety solutions. Policies, regulations, and guidance focus on fire safety statistics based on overall fire deaths and don't look at the statistics associated with vulnerable people. So if we're moving from that to the new condition, we're asking that, emergency egress is designed in the same way as we design accessibility. We want everyone to be able to self-evacuate in an ideal world. We want the occupancy profiles to be representative of a reasonable range of vulnerabilities to form the basis of design. And we want fire safety statistics to represent a range of disabilities to allow us to drive improvements in equity fire safety policy, regulations, and guidance. And finally, we want some mandatory statutory guidance so that it's enforced and it becomes a reality. So those are that's an example of shifting from current condition to new condition. And then the framework goes on to provide, in this case, 8 recommendations for how we think that could be achieved. Now, these recommendations are not an exhaustive list, but it's the first step towards making that shift. So what was happening outside of England after the Grenfell Tower fire? Well, immediately after Grenfell, the Fire Protection Research Foundation at NFPA reacted quickly to the need for globally applicable guidance for combustible cladding on existing buildings. They asked us to help them develop our risk-based approach to prioritizing retrofit in the Middle East into a freely available global assessment method specifically aimed at authority having jurisdictions all around the world. We started the work in 2017 in July, and we managed to publish in February 2018, just over 6 months later. And this guidance document is still referred to and used today all around the world. Australia had also experienced significant cladding fires. Our colleagues in Australia co-authored some of the 8 reports with the Warren Centre, influencing the future of fire safety engineering in Australia. Much of the work is equally applicable to other countries. It looks at regulation, methods, education, roles, competency, accreditation, and professional development. And this is another set of documents I would, encourage you to look at. But building design continued. We were being asked by clients to look at green facades, to look at insulating materials within the facade system, to look at the prospect of photovoltaic panels either attached or integrated in the facade system, and other combustible materials in the exterior walls. So design was going ahead as usual. Restrictions can be placed on the vertical connectivity of these materials, and we can do full-scale fire testing to try and work out what the response of the facade system would be to a fire with some confidence. But we don't really have the evidence to design knowingly. We believe that quantified risk assessment is really the way forward, but based on what? We funded a series of PhD students at Imperial College at this time to explore exterior wall fire safety and to try to bring practical solutions based on knowledge to our design teams. One project looked at the numerous variables associated with the facade design: connections, insulation, cladding, framing, additive PV panels, the different dimensions for gaps and cavities, etc. And we asked him to look at the influence of all these variables and how they came together on flammability, with the aim of using machine learning to inform prescriptive rules for our designs. And he gathered as much data as was available in the public domain to try and make sense of fire testing of large-scale facade systems. And we found some trends, and the PhD research was published, but the pool of data was really insufficient to come up with any sort of design rules. We do firmly believe that the way forward is to really make sure that all future fire tests are documented in the public domain in a digital format, so that we can use machine learning and other digital methods of interrogation to really get to a proper understanding of how fires propagate through facades, so that we can design knowingly and not rely on testing all of the time. So now, in the 2020s and next, we're very much focused on megatrends. And I would say that we are 300 fire safety engineers across the globe now, but fire safety advice is being demanded, and it's outpacing, the fire safety engineers that we have in Arup and in other organizations around the world. So our focus on this decade is on megatrends facing the built environment and our commitment to sustainability in everything that we do. This slide highlights some of those megatrends from building and mass timber to the energy transition, equitable fire safety, and aging buildings. And it also highlights the ongoing issue with combustibles and facade systems. Already, we are seeing several shifts in fire safety consulting. A significant shift is the drive towards net zero carbon. At COP26, we committed to measuring whole life carbon in all of our future projects. We developed our carbon accounting tool, Zero, and our fire safety team are feeding into this process, thinking about our impact as fire safety engineers on whole life carbon. We're working actively with our multidisciplinary engineering teams to calculate the whole life carbon of the measures that we ask for in our fire strategies, such as shown here, whether it's egress stairs, materials and wall linings, sprinkler systems, protection of structure, separation elements, fire service access roads, etc. And we are looking at this through the lens of our fire strategies and whether a building element or system is present already, so it's needed for other reasons, if we've modified it for the fire strategy, or if we added it for fire safety only, being category C. And the aim of this work is to really think about where the carbon is in our fire strategies and to adopt or adapt our approach to fire safety in response to this data. But we must also consider the impact of a fire and the post-fire repairs on carbon emissions. So it's not as straightforward as comparing the carbon of construction materials. The true value of sprinkler systems needs careful consideration, as a sprinkler-controlled fire significantly reduces the fire damage and therefore the construction repairs. Mass timber is also another approach to reducing carbon. We've been investing in timber research for decades at Arup and around the world, including for fire safety. In the early 2000s, we conducted timber compartment fire tests, again with the University of Edinburgh, to provide data for fire behaviour in small compartments, again, so 100 square metres or 1,000 square feet. And many other researchers have conducted fire tests at this sort of scale. This understanding of fire behavior in smaller residential type compartments, so like a hotel room size compartment or a living room size compartment, allowed us to develop a holistic fire strategy for the house building in Amsterdam, as seen here. The design includes detection and alarm, water mist suppression, and reinforced concrete exit stairs as some of the key components of the fire strategy. But timber is not limited to residential, and commercial developers want to build tall, open plan office buildings with the carbon benefits, but also the aesthetic and well-being benefits of exposed timber. So fire tests on the compartments at 100 square meters would not allow us to deliver timber in large commercial office buildings. So we commissioned another set of large-scale experiments with Cerib in France. These experiments use the same compartment size and shape as we used for the traveling fires, if you remember. And this allows us to make a direct comparison between the fire tests without timber on the ceiling and now with fire tests including cross-laminated timber on the ceiling. The design of the test room included cross-laminated timber on the ceiling, as I mentioned, and glulam columns, which you can probably see here. We were able to vary both the fuel load, so we had wood cribs as fuel in the test compartment, and the ventilation through the window and door openings to fully understand how the timber performed in a fire. This experimental series comprised 4 experiments, with the first occurring in March 2021 and the last in December 2021. The spread of fire across the exposed CLT ceiling was very fast and faster than current estimates would predict. This is an important insight for the design of both evacuation and firefighting response. External flaming was much longer than in the non-combustible compartment, and this has led us to reuse and evaluate external fire spread to adjacent properties, as well as fire spread vertically up the building. Once the fuel and cribs on the floor had been consumed and only glowing embers remained, as you can see here, the flaming combustion on the surface of the CLT panels also reduced through small pockets. Those small pockets continued to smolder for a significant number of hours. We had smoldering in the CLT in the ceiling and a lot of smoldering around the base of the glulam columns. 2 experiments investigated the effectiveness of protective features. So we looked at one test with a water mist system and another test with encapsulation of the parts of the ceiling. The automatic suppression system was really effective in controlling the fire, so the CLT panels did not become involved in the fire at all. The encapsulation of the CLT ceiling, or the protection of the CLT ceiling, helped to slow the fire spread compared to the unprotected test. So we now had a really good database of test evidence to allow us to design knowingly and to help our clients design large commercial office buildings with exposed timber. To provide our global team with guidance on acceptable fire strategies for common timber buildings, we developed our own in-house design guide. It's a risk-based and evidence-led and aimed at fire strategy development for low to medium-rise buildings for education, office and residential occupancies. Now, I'm aware that in North America, there are code requirements for timber buildings, but again, remember, this is not true all over the world. And for this reason, we've made this guide publicly available as well, and it can be downloaded on arup.com. Retrofits, repurpose, and reuse will also become more commonplace as the carbon cost of demolition and rebuild is too high. The work we did on the Grade A listed 188-year-old King's Theatre in Edinburgh is a really great example of refurbishing and reuse of a heritage building. The upgrade works here include 2 new cores to provide good access to all levels. These new shafts also provide an evacuation lift, resulting in a fully accessible street-to-sea arrangement for the first time. We used evacuation modeling and smoke movement studies to understand the impact of smoke layer descent on egress when a fire is located in different areas of the auditorium and stage house. And as with any existing building, we had challenges with the existing fabric of the building. One of those was that several of the heritage doors, which largely had to be retained, did not achieve the fire rating. There was missing seals and gaps between the doors. The glazing wasn't fire rated. The timber was particularly thin. Another example is of the steel that was uncovered on the project during construction being unprotected, and actually defining the fire resistance of construction in existing buildings is one of the questions that we're now regularly asked to help out with as many clients and developers seek to repurpose and reuse existing buildings. Construction of this refurbishment is underway and the theatre should be open again in 2025. The energy transition is leading to new fire safety hazards at a rate that codes and standards are struggling to keep pace with. Battery energy storage systems, hydrogen, and electric vehicles are all trends that pose fire safety hazards to buildings or communities. We have dedicated experts in these hazards to advise our clients, but probably not enough of them. If we take one of the simpler problems at the building scale, electric vehicles are becoming more and more prevalent. And we're really proud to have helped fill the gap in this area through our work for the Office for Zero Emission Vehicles in the UK. We developed interim guidance to help owners, developers, and authorities deal with the potential hazards of electric vehicles in new and existing parking structures. The guide aims to reduce risk. Suggested risk mitigation measures are given with the reasons why, so that people really understand the risk assessment approach, and case studies are provided to illustrate the solutions. Wildfire and bushfire resilience is also a growing and large field with many facets, and it's been really difficult to work out where we fit within that field and how we can really bring value. Defining the exposure and wildfire modeling or forecasting of climate change is critical in this space, but not something that we have focused on. But the vulnerability assessment and designing for resilience is something that makes use of our existing multidisciplinary skills in the built environment, and this is where we are truly focused. And we have a growing pool of global projects looking at the vulnerability of single buildings or structures and portfolios of assets for clients. And we worked with First Street Foundation in the US to try and classify the vulnerability of buildings across the whole country. Providing equitable fire safety for vulnerable people in building is arguably the most important issue of our time. The findings of the public inquiry at Grenfell have laid bare the inequities in the UK, and there's a need to address safe egress for all in new and existing buildings, and we will continue to advocate for this in the face of ageing populations. To make change, retrofits and refurbishments of existing buildings will need to invest in fire safety. We've been investigating the blockers and the opportunities for use of elevator evacuation in existing buildings, keeping the elevators running for longer via lobby protection to allow for evacuation without assistance. The feasibility of this approach is being tested as part of a desktop study across 47 properties in England. And you can see that we've found of the 47, more than 80% can be easily retrofitted with lobby protection. So as I come towards the end of the presentation, I want to talk about the next, what's coming next in the decade and beyond. The next decade will continue to be about rapid urbanization. It is expected that people live in 15-minute cities. Mixed-use buildings and developments will be common, allowing people to live, work, and socialize and interact within a local community. Carbon cost will still be a significant driver, and methods of calculating whole life carbon at a building level or per person will have matured to the point where we can develop building solutions, including fire strategies based on this data. Regenerative design will be our focus, restoring the planet rather than taking from it. Energy transformation will continue, and either battery technology will be safer or alternate fuels will be available, but there will be a legacy of battery energy storage systems. Autonomous vehicles such as drones will become more common. Small urban airports will be found in our city centres. We're already designing these today, and they are a hybrid between a terminal and an aircraft hangar in the middle of a city. Aging populations will become even more apparent and increase our focus on design solutions for vulnerable people. Urbanization in the global south and the Middle East will accelerate, and giga projects will commence. Building in timber at scale for low and medium-rise buildings is likely to continue in Europe and North America, where timber is readily available. The UK market will follow, but it will take some time in the wake of the Grenfell Tower fire. Refurbishment and retrofits of existing buildings will become commonplace. And all of these need a fire safety consultant. They all need total fire engineering. And the role of them and the importance of the fire safety consultant will continue to grow. But I want to end by emphasizing that we are all accountable for delivering fire safety on our projects. Architects and engineers of all disciplines have a key role to play in delivering equitable fire safety. And I'd ask you to think about this, perhaps download the change framework that I've talked about today, and reach out to me in the future if you'd like to discuss anything further. And with that, I'll hand back to Silvio.
Introducing
Okay.
the next speaker.
Thank you, Susan, for that presentation. Just moving along with our NORR, I'd like to bring on Birgitta Messerschmidt, is the Director of Research, the National Fire Prevention Association. She's responsible for NFPA's research strategy, research on fire problems and other safety issues, data collection efforts to maintain NFPA's fire incident and fire service databases, and NFPA Research Library. She has a Master's of Science in Civil Engineering from the Technical University of Denmark and has spent her entire career working on fire safety issues. In the early part of her career, she focused on fire testing and how the performance of different products can impact fire development. She was involved in the development and implementation of harmonized EU fire testing and classification systems for construction products. Other areas include fire performance of facades, fire toxicity, firefighting health and safety, fire resilience of built environment, fires in wildland, urban interface, and fire data collection and analysis. She's been active in international standardization, has advocated for fire safety policies around the world. She has published and presented numerous papers on fire safety issues. Please welcome Birgitta. Can you please come on?
Thank you so much, Silvio, for inviting me here today. And thank you, Susan, for an amazing presentation. Really fascinating to hear the full story of 50 years of fire safety engineering at Arup and how that has impacted the world. I'm going to start out talking to you about the structural fire engineering. There's two reasons for that. One, of course, is it was the earlier part of your presentation, but also because when I studied engineering back in Denmark in the early 90s, we did not have a fire engineering degree, but there was one course in structural fire engineering that I found so fascinating when I took it that it inspired me to do my master thesis in structural fire engineering, which then led to my first job in the National Fire Lab in Denmark. and then led to a 30-year career in fire. So I have a bit of a fondness for the structural fire engineering. So really what I'm curious to hear is that has structural fire engineering become mainstream since all the work that you did on it there in the 80s, 90s, so that the response to fire is part of the structural design for all or most buildings, or do the tabulated data and codes still prevail?
Yeah, I mean, realistically, the thousands upon thousands of buildings that go up all around the world, the tabulated data does still prevail. Structural fire engineering is relatively commonplace in the UK or England for some commercial office buildings, but it very much still sits within a small group of technical experts. So your structural engineering teams all around the world are not, designing for fire in the way that I described. The codes and standards provide some guidance on how to do it. So the Eurocodes and now ASCE SEI 7-16 talks about how to do it and how a structural engineer could go about structural fire engineering. So, there's knowledge, there's guidance, but it's not commonplace by structural engineers by any means. And I think that's partly down to, there just isn't enough university courses. The prescriptive solutions don't require it. The codes and regulations don't require it necessarily.
So what you're saying is that course that actually inspired me back in the mid to mid 90s was unique, huh?
Yeah, no, definitely. It is very unique. Realistically, the number of fire engineering courses around the world to train the fire safety engineers of the future are also, becoming less, actually. There's less schools doing that now.
That is really sad, considering how you talked about how things are definitely needing fire safety engineers going forward. So then I want to move on and then talk about our concept of total fire engineering. I'm curious because I really like the idea, and I think it's absolutely critical for us to have the fire safety that we plan for and that we want from our regulations and codes and so on. But is it embraced by your clients in general? Are they involving you in all stages of the building design, construction, and maintenance?
This really varies from country to country, client to client, project to project. So where fire safety is really critical, say in a hospital or in an airport where, continued operation is very important, then yes, we will tend to be appointed all the way through. For simpler buildings, we may only be appointed for the concepts, or we might only be brought in because there's a problem. So, it does really vary. I think across regulations. So Ireland, as an example, regulates that the fire safety engineer has to be involved across all stages of certain projects now. I can see that beginning to happen maybe in England. And certainly in the US, it is mandated in certain states, but it's really variable across the world.
So this is really an area where you can say that the codes and standards have not yet adopted this widespread.
Not enforcing it, yeah.
And therefore, we do not see it so often. Fire safety engineers are just brought on as you say, well, here's a problem, come and solve it, instead of being part of that whole strategy all the way through.
Yeah, that can be the case for sure.
That is really sad to hear. I must admit. I guess I naively thought, listening to you, is like, well, of course, everybody must be doing this. This sounds like the way to go forward and ensuring the safety. But yeah, I must admit that really made me sad to hear.
Yeah. Okay, we have delivered some amazing projects, but yeah.
Yeah. Brigitte, I just want to touch a bit on what you just brought up. I think that Susan, you've done an amazing job in covering the entire history, but I want to just touch on that. When you look at the affordable housing crisis that's happening across the world, I think those are the kind of projects that are very difficult to actually see a fire protection engineer there from start to finish. I think those are the kind of projects that tend to bring a fire protection engineer in and out only. And as Brigitte has alluded to, only when there's a problem. Would you agree with that? And especially in the way that some of those projects are actually delivered in their delivery method.
Yeah, I think there's almost a perception that, you know, a simple residential building doesn't need that fire engineer. And, you know, in some cases, maybe that's true if the architect or other member or all of the members of the, you know, the design and client team are very familiar with the codes and know what they're doing. That could be true. But yeah, I would agree with you. And I think especially when it comes to maybe retrofit or repurpose of existing buildings to social housing, the complexity of that is really significant and probably does need the fire safety engineer to, you know, help steer the design team through an appropriate fire strategy.
Well, and especially as you talked about at the end of your presentation around the new emerging issues that are coming in. These will be also in residential buildings.
Sure.
So even though we might traditionally have thought of those as well, they can just follow the recipe in the code and you can make a residential building fairly simple, etc. With all of these challenges coming in with the electrification, battery energy storage systems, with people bringing their micromobility into their apartments, etc., etc., how can we not bring in fire safety engineers early in those projects? Because the codes are not yet ready to deal with some of these challenges. So I really think we need to rethink this a little bit.
No, I 100% agree. And I think we need to increase the number of schools that are providing that education, whether it's to a fire safety engineering level or just more education to, you know, some of our listeners, the architects and the other design disciplines.
I would totally, Brigitte, I totally agree with what you just said. I can tell you that in Canada, you know, we're looking at upgrading, you know, building codes, and you know, we're currently working on the new code for 2030, and a lot of the things that you just brought up about scooters and electrification of things that are ending up in housing currently are things that, you know, we're looking at upgrading the code to, but it still hasn't happened. You're absolutely right. All of these things, as soon as Susan has talked about, the mega trends that are currently hitting us right now are not part of the code. I mean, because we're still grappling with it in the building codes, and it may not hit the 2030 code, it may not hit the 2035 code, it may not hit us until 2040. So, you know, the standards aren't even there. So having, you know, a fire protection engineer as part of the team is extremely important.
Yeah.
Exactly. I mean, this is what I always say to people. Remember that codes and standards are based on looking back. They're based on what we've learned through history with events, fires, etc. What were successes, what were failures, and we're not yet at a critical mass with a lot of these new emerging technologies that we've seen enough events for us to make those changes. They are coming, they are happening, and you know, Grenfell, of course, is a sad example of how we can see rapid changes to codes and regulations based on a disaster. But Susan, I want to you know, I can't sit here and discuss with you on fire safety without also bring in facade fire safety, and you talked about it quite a lot. And you and I, we work closely together on NFPA's facade risk assessment tool. Now, you pointed out in your presentation how Arup, as part of total fire engineering, were advocating for the careful use of insulation materials in building envelopes due to the energy targets set by the building regulations in the UK, Europe, USA, and elsewhere that were resulting in use of highly insulating foams in exterior walls. Now, this, as you said, led for Arup to be seen as somebody who was preventing sustainable design solutions. Do you find that there's a lack of understanding of how insulation can impact the fire performance of facades, and that this can cause a conflict between fire safety and energy efficiency?
Yeah, I think, you know, foam insulation, well, to be honest, I think understanding how materials perform in fire, whether it's insulation or cladding or an internal lining, is actually misunderstood and not clearly understood by the people specifying those products. You know, the testing for combustibility, flame spread, toxicity, smoke production, there's a lot of testing required now. And quite frankly, some of the suppliers are advertising their products as being fire resistant or, you know, fire retardant without clearly necessarily explaining what that means. And it's confusing for architects and facade engineers. I mean, if I think about historically, your materials of construction were so much more simpler. It was brick, it was mineral wool, it was steel, it was concrete, it was timber maybe, but everyone understood that timber burns. Nowadays, you've got composite materials, you've got these insulations, and some of them are used to achieve sustainability targets, and some of them are just used to make the building lighter or, you know, more or easier to build. And it's a bit of a minefield, even for fire safety engineers who really, you know, have studied the field. So I do think that we have a lot of education to do around understanding how materials perform in fire, regardless of what building system they happen to be in. And that is going to be one of the, we don't want a knee-jerk reaction where we just say no to a product. We need to understand how it performs so that we can help, you know, clients deliver more sustainable buildings. But we need to do it carefully and knowingly. And yeah, I don't want to be the person saying no to all the sustainable solutions, but we do need to do it together and think about it properly.
Exactly. I do sometimes find that we in the fire community becomes just the no people.
Yeah.
You can't do that. Oh, it burns. And I keep trying saying, if I am lucky enough to present at either a green build or AIA, say no. What we want to do is work with you to make sustainable solutions fire safe. I think that's truly important. But in the line of what we were talking about before with codes and standards being developed based on looking back and can't keep up with the modern or emerging issues, do you find that they can keep up with those new materials you were mentioning as well, considering some of the fire test methods, for instance, for fire resistance that we use was developed more than 100 years ago based on non-combustible materials? Our flame spread method here in North America, the Steiner tunnel, was based on testing wood. And now we're doing all these interesting materials instead that we're trying to test in ways that might not be reflecting the risk that we see. So what are your thoughts on that?
I think we just have to be really careful that we don't design out with our knowledge. So I would be really uncomfortable designing a facade system on a super high-rise building if I was relying on the test results. I want to know whether that, if I have an instinct or, you know, I can calculate that facade will perform well in a fire. I don't want to rely on a bespoke fire test all the time. So I think that's where we need to get to. We need to, I mean, structural engineers design knowingly. They calculate the load that the steel frame will carry. And that's where we need to be in fire as well, I think. Otherwise, we don't know where our safety margins are.
I couldn't agree more. That's always my I have a dream speech, that we get to that point in safety, right?
Maybe not in our career.
Yeah, probably not. But all right. So I'm moving from that on to one of those new emerging topics that you were talking about, the carbon. And the net zero carbon that you're working towards and your dedication to sustainability, etc. I find that the carbon discussions related to fire is always focused on lowering carbon in fire protective systems. For instance, the sprinkler pipes. But the benefits of fire protection systems or using fire protective products in other applications, for instance, the facade systems we just talked about, is not considered in carbon calculations as far as I know. And you were mentioning it just quickly in your presentations, how sprinkler systems can prevent a fire and thereby help prevent carbon being released. But has ARA found a way to include the positive impact on carbon from preventing or limiting fires?
I wish we had. We haven't. I think I think we could calculate, you know, if you've designed a sprinkler system for the building, you could calculate the expected damage and therefore the expected carbon cost of retrofits of that sprinkler protected building versus, you know, more significant damage if the fire was allowed to spread. The problem is, how do you define whether a fire is likely to occur or not? Some clients go through an entire lifetime without having, you know, a fire in their building of any significance is dealt with an extinguisher or whatever. So it's that, I think that's what we're always dealing with, is unless you've actually been impacted by a fire, it's difficult to measure the value of a sprinkler system. I know clients who've had fires are much more likely to ask us to put that extra level of protection in. But it's an interesting question. It's something we'd like to do.
And I could just imagine Arup being the people doing this because you're working across the field of sustainability and fire safety. So that's why I was provoking you a little bit with that one.
Next project.
Yes, next project. I would love that, right? But staying with the carbon topic, let's talk about wood a little bit. I'm so impressed with all the research that you've done at Arup to understand the impact of mass timber on fire safety. Your large-scale compartment test there is truly fascinating. And then you even made that, you know, the guidance that you developed based on this, you didn't just keep it in-house. You actually made it public so all of us can use it. Do you think it will increase the use of mass timber and potentially even bring mass timber into UK at scale, getting over this fear from that Grenfell has put in the UK?
Well, I mean, so the code red experiments that I talked about are talked a lot about, or you know, a lot of people talk about them in the public domain. Authorities having jurisdiction, insurers are very familiar with them, especially in the UK, and it has made our work much easier. And I'm sure it will have a ripple effect with other designers and consultants. It's probably not enough for the UK to rapidly, you know, adopt timber, but it's one part of the or it's one step on that journey, I think, and hopefully it's a significant step. We are very proud of those tests and the guide.
You should be. Great work that definitely will help in making sure that the mass timber is used safely around the world. So last point that I wanted to touch upon is the change framework developed by Arup based on the report that Dr. Barbara Lane did to the Grenfell inquiry. And naturally, this is focused on the situation in England, but I am curious if you would consider making it more globally applicable.
So I mean, it's definitely globally applicable already. I mean, it's written in the context of England, but if you kind of remove some of those or don't read it like that, it's equally applicable in many countries around the world. And it's again, it's a first step. You know, the recommendations in there and even all the elements maybe are not everything that needs to happen, but it's a first step towards improving fire safety across England. But yeah, it's definitely for sure globally applicable there.
So now I'm going to be a little selfish and bring in because as you know very well, NFPA did the fire and life safety ecosystem, which describes 8 components that each play a critical role in protecting people and property. How do you see the change framework that you have made in comparison or complementing the NFPA fire and life safety ecosystem? Do you see them work together?
Yeah, it very much complements that. I mean, your ecosystem, which we quote a lot, we talk about a lot with our clients. We even looked at it while we were doing the change framework, is a full ecosystem. It has all the cogs of fire safety that a community or a government or need to look at to see that, you know, they're delivering fire safety holistically in their community or city. I think our change framework doesn't address it, but all of those elements quite so holistically, but they're very much complementary. And people should have a look at your ecosystem. It's a really simple, easy concept to grasp and reminds you that fire safety is not not just about the codes and standards, it's about much more. It's about the whole system.
For anyone who is curious, you can find it at nfpa.org/ecosystem. So thank you, Susan. I think I would love to work with you on where we can try and mix those two together and see what we can find of interesting synergies between the two. I could continue chatting with Susan for hours, but I don't know if it's time for us to maybe consider some questions for audience.
Brigitte, I wanted to ask you. Obviously, Susan, you've done a lot of testing. You've obviously testing, and this is research and testing that a lot of firms, and certainly you're one of the largest firms in the world, and it's and you've got some pretty incredible projects, going all the way back to the Pompidou Center, where it's possible to do that. A lot of firms don't have that ability to do research and Brigitte, with NFPA, how do you look at the world of fire protection, and how is the world actually dealing with that? And we look at architecture and engineering, and we look at all of the different, and certainly with NORR, we've had a lot of people on, and architecture and engineering is going in a lot of different directions, but fire protection engineering is not one of those where you want to go a million different directions. How do we bring fire protection engineering to the forefront, and look at the different countries and bring some focus to it, so that you take for instance Canada, where every province had its own code. Everybody was going in a different direction, and fortunately now they're coming to their senses, where one entity is actually going to deal with codes. But everybody seems to be doing their own thing. They're all doing different measures, but there's no cohesiveness in the world in dealing with building codes, building standards, how materials, and you've touched on this, Susan, where companies are able to put products out into the market and say that they're safe, and they're in the market. And even for architects trying to look at the standards, whether or not they're capable of meeting standards, it's very difficult. And there isn't an entity worldwide where you can actually look at, other than focusing on the area that you're in, the local area that you're in, and they may not even be 100%. I don't know, Brigitte, whether you want to take that question, or Susan.
I will start at least. I think this is one of the complicated things that we have, right? That every country do things their own way. Looking back to where I started my career in around the harmonization in Europe, what we could do back then, and what we was successful in doing, was to harmonize the way at least we tested and classified construction products. So we at least spoke the same language around that, about product performance. But it was still up to every member state to have their own fire regulations, fire codes. So how they would reference this, what they would require in different applications. And as you move around the world, that only gets even more and more complicated. In the US, even though when I moved over here 23 years ago, I thought, well, it's going to be a lot easier, it's one big country. And I realized, no, it's a lot more complicated, because every state do different things. And even though we have model code, somebody might use a model code from 2012, another one from 2020. Somebody might not have anything. Major cities might do their own thing. So unfortunately, I don't have much hope of us doing any globalized harmonization on the code side. What we are doing is try to keep the focus on the ecosystem, actually making sure that you have the codes and standards, and that you make sure that they're developed, that they're updated when there are new things happening, that you are then also using the reference standards that are there. So if your code asks for fire test, you are actually looking at results from the correct fire test and not something that was done to other requirements that doesn't fit with what is in your jurisdiction. So we try to make this a part of what people are thinking when it comes to fire safety. And as much as I would love to see NFPA codes and standards used around the world, I don't think it's going to happen that we will be the only ones providing fire safety standards around the world.
Susan, your thoughts?
Yeah, I'd agree with Brigitte. I mean, the politics around writing codes and standards internationally and the risk appetite of different jurisdictions varies too much for us to have one global code ever, I think. But it's like when I'm designing from first principles, or when I'm even, teaching some of our younger teams, I say, right, just put the code down, think about what we're doing, think about the first principles. You want to tell people that there's a fire, you want to get them out, so you want some diverse escape routes. What materials is the architect proposing? Are they combustible? So just think about things from first principles for a while, because fires are the same all over the world. They're not any different. Yeah. And the intent of all the codes and standards around the world are the same. The intent is to allow people to be warned about a fire and to escape, and for the building to remain standing unless it's very small. So that's how I think about it.
Yeah, the whole subject of education. You mentioned that there are the universities and the schools are struggling with that. Can you talk a little bit about that?
Yeah, I mean, we've seen, there's a handful of universities around the world who actually teach fire protection engineering. North America is probably the most prevalent. I've seen schools in England closing in the last few years. There isn't enough schools to educate the number of fire safety engineers that we need in the built environment for all the hazards that I've talked about. And I'm working with some international colleagues in the Society of Fire Protection Engineers. NFPA is also represented, to try and work out how we change that and raise awareness maybe of fire safety as a career at school age, and talk about it much more, about how important it is. Because when you're at school, you really learn about engineering, but not these more specialist things. So we've got a lot of work to do. But I also firmly believe that everyone in the built environment, involved in the built environment, needs to educate themselves in fire safety, because we're not going to be able to do it alone.
Have you seen a tendency for architects to kind of leave it off to the fire safety engineers to worry about it and say, this is not my jurisdiction, it's a specialist, we're going to bring in the specialist, we're going to bring in Susan because she knows it all, and we don't have to know about it? Have you seen that become more prevalent over the last 20 years?
I think as it's got more difficult, it's, like the construction materials, and defining whether construction materials are safe or not has definitely caused a bit of an issue there, because it's become too complicated. I've heard architects say to me, like older architects say, 30 years ago I could do this myself, Susan, but now I have to have a fire safety engineer. And I think once they're on the project, there is maybe a tendency to step back a bit. But the reality is that a fire safety engineer isn't as involved or as embedded in the project as an architect. As an architect tends to know every single thing about their building, what every single selection of material, down to the real details. And we have to collaborate and coordinate. And, architects still come to me today and say, Susan, you need to have a look at this. So they are still thinking about it and worried, about aspects of the design that they want to have checked. Again, it's variable. Yeah.
I tend to see as I said before, the Pompidou centers and the Shard and the big projects there. I probably a little easier to deal with than the smaller projects. I think the smaller projects get lost, and the affordable housing projects seem to get lost. Not so much the hospitals, because I think the hospitals are those projects are a little bit more in control.
Yeah.
But it's the smaller projects that things get changed and get value engineered. I mean, how many value engineer proposals do you tend to see on the smaller projects, because they probably have the most difficult budgets,
Yeah.
as you move through those projects.
Yeah, and that's when design decisions are made very, very quickly, and mistakes can be made. Yeah.
Yeah. I'm going to bring on Kevin Cooper, who is director in our Glasgow office. Kevin, can you join us, please?
Yep. Hi, everybody. How you doing?
And Kevin, I think you probably have some questions, and you also have some questions from the audience. So maybe if you want to join in, questions of yours and questions of the audience.
Sure, absolutely. Yeah, there's quite a few. So, first of all, Susan, this kind of design knowingly thing's quite interesting, because I had a question from one of my colleagues. I was talking to him earlier today. A kind of real sort of detailed question that maybe resonates with most of the audience. So, as you said, things have got a lot more complicated over the last 30 years. So we've got colleagues who are obviously, at the coalface designing details. And there's almost a kind of infinite number of details, in a wall construction that there's a whole host of different issues that affect it. And things like passive house considerations now kind of sort of flow into that as well. So I suppose the question is that, there seems an almost sort of infinite number of possibilities in terms of design and technical detailing versus much more limited number of sort of certified constructions, as it were. So what we find is that in dealing with building control, if you're trying to do a certain wall arrangement and it doesn't exactly match, a specific testing, then it creates issues with building control.
Yeah.
It's just so there's lots of detailed issues like that do seem to sort of cause a problem. But what you were talking about in terms of design knowingly, I don't know, what is the answer to that? Because it's something I think causes a lot of frustration and delays projects, and I'm not quite sure how you solve it, other than getting the expert input of somebody like yourself.
Yeah, I think my experience of in England in particular after Grenfell is that a lot of people are now asking the fire safety engineer to look at everything to the nth detail. It could be, do we need to put extra fire protection on that bit of steel because we've connected something to it? Or like really detailed questions about how a compartment wall abuts a column or some awkward detail, which we wouldn't have been asked before. And I think it's about liability, it's about consequences. There's an anxiety, I think. And I feel we're at risk of, like, we can't test everything. We can't calculate absolutely everything. We are going to have to rely on our experience and common sense, for some of these solutions. For the facade problem, where we have, you maybe have 10 different wall systems because you've got, slightly different details. Again, if we had calculation methods and all this data that I was talking about that we could start to interrogate to come up with those calculation methods, then we wouldn't need to test the 10 scenarios anymore. The problem we're in right now is we don't know if that facade system is going to pass the test or not, unless it's almost all non-combustible construction. So yeah, we are in a bit of a difficult period, I would say, and I don't really have the answers other than we are going to have to try and better understand how some of these more complex systems behave so that we can make judgment calls without doing another really expensive large test. But I also think that we need to be much better at demanding facade skill tests when we need them. Like, when we're designing tall buildings for wind, there's large scale tests for wind, there's large scale tests for other loads. And I think there's this perception that, oh, a fire test costs too much money, why do we need to do that? So we need to get better at asking for it as well.
Yeah, and as Silvio touched on, I think if you're doing, a skyscraper in Manhattan, and all of those tests, I guess, will follow. If you're doing a sort of design and build school in Scotland or England, where the budget is a lot more challenging, then, it is difficult. And you do get, a lot of building control officers that do apply a lot of common sense, and then others that are more difficult. And it's almost kind of demanding that the wall construction must be exactly as per,
Yeah.
that certificate. So it's tricky.
And that's when you may need to bring in a fire safety consultant to talk about it. I think for the social housing and the schools, we need to get smarter about really trying to limit the number of facade iterations that we have, and design 10 buildings or 20 buildings that are the same. There are ways around that kind of thing.
Yeah, you tend to with those social housing and some of the schools, you tend to probably have the most imaginative architects trying to do the most imaginative schemes, because they're looking forward to the next design award for those projects. So as you say, Susan, trying to do the most common details and trying to do it probably doesn't necessarily work. You're constantly seeing schemes that are a bit out there, and they're looking at new materials, and they tend to be a little bit more risk adverse.
Yeah, there's various questions in the feed here. One of them was about there's obviously a lot of sort of digital simulation you get in all sorts of aspects of design, but I suppose essentially what they're asking is it ever going? Are you ever going to be able to go beyond kind of real world tests? In terms of if you need to test a fire scenario, then I guess you've sort of got to do it physically, because I imagine that might throw up things that you wouldn't necessarily see in that kind of
the problem with modeling. So modeling fire is actually very difficult because it's a hugely complex chemical and physics problem. So even modeling without introducing the complexity of a facade system that's burning and bits are falling off and the flames are trying to get through cavities and whatnot. So we can model fires in large atriums and that kind of thing really well. That's been done for years because that's essentially just computational fluid dynamics. But once you start trying to predict how a facade system will perform, or modular construction will perform, or just a lightweight timber or a lightweight steel panel wall system will perform in fire, it's really difficult to model that. And I think once the computing power is there and we can do endless Monte Carlo simulations of any possible situation, then maybe we will get there, but it is complicated.
I've seen, just to comment on that, I've seen recently some interesting work that seems to be going on around hybrid testing and digital. So hybrid modeling and testing. So as you are testing part of a structural element, your model in real time how that impacts other parts, and potentially if you then do several simultaneous tests on different structural elements, try to connect that. It's in its early phases, but it just sounds really interesting because it would be able to expand what we could learn from some of the fire tests.
Yeah, definitely. And I think if we get this rich data from fire tests into a digital format that, you can really trawl through AI or machine learning or all these techniques, then I think, the future is there. But we as, the engineers of today need to try and get that data available for the future. That's our biggest problem. I mean, Birgitte, this data in fire is.
I almost asked you about this, Susan, because that is a huge problem that we see, that large scale tests are expensive, and you only have to pass one test, and then the system that you've tested is then the one that can be approved. Nobody knows about the 99 tests you did before where you failed. So nobody knows what it is, those little details that you changed in order to get the performance that you wanted. If we had this kind of information in the fire safety community, as Susan says, then we could use machine learning to go through to help us design better systems. So when somebody in the design phase says, well, we really would like to change this detail, we might say, hey, this was tried, it doesn't work. We don't know.
Yeah, it's quite frustrating.
Yes.
Imagine. See, on Grenfell, I mean, a really terrible, shocking tragedy, and there's obviously all sorts of, numerous issues associated with it. But it struck me that, as someone who designs in Scotland, in England, there just seemed to be one means of escape from that building, a much more sort of fundamental level. And I don't know, is that something you come across quite a lot in higher rise buildings? It just seems kind of quite shocking that it would only have one means of escape, which surely by its very nature is a terrible place to start in terms of fire safety.
Yeah, the single stair debate. So that is being debated all over the world. Typically in the jurisdictions I work in the Middle East and in the US, you'd be allowed up to about 4 stories with a single stair and a very small footprint.
Yeah.
Look, I'm kind of leaning towards having 2 exits most of the time. I think that it's perfectly reasonable to have those 2 exits, but I think under certain conditions you can design a building that's safe with a single exit. It's just that everyone who's doing that design needs to buy into the fire strategy and make sure that their aspect of the design is done well, it's built properly, it's commissioned properly, and it's maintained properly. But I mean, that's also true of a 2-stair building because, if that's not maintained either. So I don't know the answer to this, but I do know that it's being debated at great length. And I do understand as we try to repurpose buildings or build in more and more crowded cities with smaller and smaller footprints, adding 2 staircases takes up a lot of space. So the debate will continue, I think. Brigitte, I don't know if you have a view on that.
No, I agree with you, and it's definitely a discussion that goes on quite quite hectic here in North America at the moment around the single exit staircase because people want to go up to a few more stories in order to and still have single exit staircase. But one thing I was wondering, you were talking about in your presentation around using, the elevators for as a means for escape. Is that a way to solve this problem around single exit stairs?
Yeah, I think potentially, as long as we can, the big problem with the elevators is just the reliability of them. We've got to make sure that the water doesn't get into them, that the power is available, etc., and also change the mindset of people occupying buildings that the elevator is safe to use. So I do hope that elevators become part of the egress solution for buildings, and then we should look at whether we need 2 or 3 stairs then, or we can do something different. So yeah, all of that is up for debate. I think in any single stair building, I'd be leaning towards having a sprinkler system so that you have to have a certain level of safety, and if you're reducing one aspect, and you have to increase another.
Exactly. It's not like just taking away an exit stair and then continue with the same requirements you had before. No, then you gotta, add in other places.
And the height of the building obviously makes an enormous difference.
Exactly.
Yeah.
But I would say it was a shock when discussing Grenfell here in the US. Most people think, how could they only have one single stair in that building, right? Because that wouldn't happen here. So it was a shock.
The principles of fire safety though in the US and England are very different. So England was relying on non-combustible construction and compartments, no sprinklers and 1 stair with smoke control. In the US, you'd have sprinklers.
Very true.
It's different. Yeah.
Very different fire safety strategies. Exactly.
Very different fire safety code. Yeah.
What in your experience, just out of curiosity, what in your experience, I mean, I guess it's maybe difficult to compare apples with apples, as it were, but which country do you think has actually got the best codes, or do they all just vary so much that it's impossible to say? And what do you feel most comfortable? Which environment do you feel most comfortable designing in?
I think this is the answer to this question is based on our own biases, and it's hard, to. And I think, I work in Africa where the UK codes are more prevalent. I work in the Middle East where the US codes are more prevalent. I personally am a massive fan of sprinklers because the sprinkler system is one system. It takes one set of maintenance people to maintain it and do the testing on a regular basis. And if in 5, 10, 20 years someone comes along and damages a fire door, or the fire stopping is no longer available because someone's pulled it out and hasn't replaced it, the sprinklers give you some real resilience, I think, and we need to sort of find a way of measuring that. Whereas if you're completely relying on compartmentation and you don't have that sprinkler system, then there's so many things can go wrong over the lifetime of a building, and you need people to be inspecting and identifying the problem and then getting it fixed. And that could be anything from fire stopping to fire doors to adding, combustible materials by accident to some new part of the building, or whatever the issue is. I like the fact that the sprinkler system is one system and you can rely on it if it's tested and maintained. It's not 100% either. And that's why we have layers of fire safety in buildings. But I do think that some aspects of a fire strategy are easier to maintain than others.
Yeah, I mean, if you've got a sprinkler system, I mean, it sounds a daft question, but presumably the likelihood of a major fire is significantly less than you would have thought.
Yeah.
No.
And I think we could do with more data to prove that. So I suppose I didn't really answer your question, but I do lean towards the US codes, I'll be honest, because they are regularly maintained every 3 years as well. There's a whole kind of robustness around them. And, the Middle East has adopted them, in parts of India have adopted them, and there's reasons for that.
But I guess there's a kind of history there of larger, taller buildings.
Larger, taller buildings, yeah, it's more appropriate to probably follow the US. But with any code and standard, if it's followed properly and the intent of the code and standard is clearly understood and you're following those first principles of fire safety, then, you can build safe buildings anywhere.
Mm-hmm. Sure. Yeah.
Kevin, maybe we should move on to the questions from the audience.
Yeah, no, there's I've sprinkled in a couple there.
Oh, you had, okay.
Already, yeah. So I'm just multitasking. And one of the questions here is a question about what strategies are in place for fire protection during construction from an insurance perspective.
Okay.
Because again, I suppose it really depends on the complexity of the building and sort of what stage it's at. But
yeah, I mean, I think this varies country to country. Here in the UAE, there is a whole section in the UAE fire code that asks the contractor to have certain provisions in place during construction. So the wet standpipe system has to be in place before they go up above a certain number of stories, that kind of thing. I think in timber construction, this becomes really important, or if you are installing combustible construction materials, it becomes really important because you need to make sure that you don't have, I think the question is alluding to having a very large construction fire because you're either storing construction materials on the site or they're in the building before, say, the sprinkler system is active. And I think insurers are becoming more and more aware of that. And it is one of the problems for timber construction, I think.
So can I would love to just join in on that one because I mean, we've seen a lot of big fires here in the US in buildings during construction, especially multifamily buildings up to 4 or 5 stories built in lightweight timber. So I would say one of the things I would advise you to is look at NFPA 241, which is fire safety during construction and renovation. And that brings me to it's not just a challenge with ensuring fire protection during construction. It's also when we renovate or retrofit existing buildings, which, as Susan was mentioning in her presentation, is one of those mega trends we see. It is something we really need to think about and not just think, well, everything is okay because the building is already standing.
Yeah, no, there needs to be a management strategy around fire safety, just like there's one around health and safety of the construction sites.
Yeah, sure.
Yeah.
No, I must say, in my experience, anything made of timber, whether it's during construction or on completion, seems to cause problems with insurance. But what else have we got here? Just conscious of time. One of my colleagues, David, is asking, how do you see the creation of a body of professional fire engineers in the UK affecting your work? I don't know if that's perhaps one of the suggestions from the Grenfell
Inquiry. Yeah. Well, I mean, I think it's sort of overdue. I'm a chartered fire engineer. The professional engineering status in the US, and there's an equivalent in Canada. I think it's really important. I mean, so when you're designing a building, the codes worry about structural safety, electrical safety, and fire safety. And fire safety engineering as a profession is not treated in the same way as the other two, and it should be. So we definitely should have a recognition of it as a professional engineering entity. We're going to have to fill those roles through education and through schooling, but I'm all for it.
No, that's Brigitte. I presume you would agree with that.
Yes. No further comments.
Okay, what else have we got? I just wondered, Susan, perhaps if you, in terms of the, so again, this is maybe a sort of UK biased question. We've got the new Building Safety Act that's come out in England, which seems to have addressed a fair proportion of the Grenfell things, although I understand there's a lot more needs done. Some of that arguably, I guess, was already addressed in Scotland, but I was just keen to maybe understand a little bit more about your thoughts on that, and what other things, if anything, you think need done to sort of improve, or what benefit, what's your thoughts on how it's improved the sort of wider status of the construction industry, I suppose.
Okay, with the caveat that I don't work in the UK on a regular basis because I am sitting here in the Middle East. What I understand from my colleagues, and I helped write the recommendations report for the inquiry. The Building Safety Act has gone a long way in addressing some of the issues arising from Grenfell. I mean, there's much more stringent requirements. There's enforcement for these higher risk buildings. So, it's definitely improvements. How it will be enforced, managed, what the outcome of that will be in 10, 20 years is to be seen. I mean, the change framework that I talked about talks about the things that need to be done beyond that. So, the elements that we talked about the current condition and what needs to change to create the new future condition. So that's our response to that, is that the Building Safety Act goes so far, but our change framework is where is what we think needs to happen next.
Okay, I think we'll just coming up to 5-2, Silvio.
So one question, Susan, what's happening, I think, it's certainly happening here in Canada, and I think it's happening to a certain extent in the US, and a lot of it touches on housing affordability. Social housing is part of that, and it comes out of COVID and the fact that and our office and perhaps your office as well, people are working now from home, and we have a overabundance of office buildings that are pretty much almost vacant, and people are looking at conversions of office buildings into housing predominantly. So we're looking at retrofit and reuse of commercial buildings into housing. The Canadian government, who is the largest building owner in Canada, is going through the same thing and looking at converting their office spaces into affordable housing. So we're at the start, I think, of or in the middle, or definitely well into conversions, retrofits of buildings that were built for one use and now are going to be converted to something completely different, which is going to completely affect, not only exiting, but how these buildings were originally actually created. Can you talk a little bit about that and how that's going to happen? Because they're actually doing all of this, but these buildings exist and they're going to have to be converted into something else because they're not going to be sitting there and left vacant. So that's going to be a whole, I think in the built environment is going to be a whole industry on its own.
Yeah, no, I'd agree. And I think, I mean, understanding the baseline fire performance of the building just to start with. So, you know, what fire resistance do you have in the structure? If you're going to rely on any of the systems, what states are they in? So there's a whole piece of work around that. And then, you know, the design of a residential building is quite different than a commercial. So there will be a lot of change to that. I mean, you'll be introducing corridors and compartment walls for flats, but it's kind of it's an interesting problem. And I think, you know, if they were doing it at scale, you need to kind of work out what those challenges and principles and methods of working and workflow are for, say, a typical situation, and then try and work out how that would be applied at scale. So I think the scale problem is really interesting. And it's important that we do it well, because there will be vulnerable people in these buildings. And I've already talked about that at length in my presentation.
Yeah, and these buildings are all going to be pretty much one-off. I mean, there's no one solution will
No.
work for all the buildings. So it's going to be an interesting dilemma that you know, I know Canada will have. I think the US will have the same thing, and I'm sure the UK will as well, and the rest of the world.
I think this speaks to the importance, as Susan has mentioned, both during her presentation and also here in the discussion, around making sure that this fire safety strategy is documented. Because as we're thinking about buildings being built today and how they might also change their use going forward, we need to know what was the fire safety strategy for this building, what was it based on, so that if you do change the occupancy of that building, if you change the building to complete different use, you know where to start. You have your baseline, as Susan was talking about. So therefore, and then you can start building towards having it safe in this new function that we want it to have. But it's all documentation.
Yeah, that's the golden thread that we talk about. And hopefully building information modeling and, you know, the different ways of working will make that easier for the future, rather than looking for a piece of paper from 20 years ago.
Yeah. Brigitte, that's a very, very good point. It's probably a good place to end this session, because it's probably the key to the built environment. These are buildings that were built at different times, certainly the past ones, and to your point, the buildings that we're building today. You know, what is that plan, and what was that plan, and you know, what can you do with it? And without that roadmap, that plan, it's pretty hard to do anything with these buildings. I mean, Kevin and I, our firm has done a lot of adaptive reuse buildings, and it's always very, very difficult to go in there and do your forensics on the building, because there's nothing to start with, you know, day one. So you know, and it's pretty hard to go in there and start ripping things out. I mean, clients aren't too happy when you start to do the destructive research on a building and tearing walls out, but you almost have to do that to really try to understand what protective measures were there for the steel that's inside the wall that's hidden. Yeah. So, Susan, thank you very much for this session. It's this is a huge subject for architects and engineers, and this discipline that I think that, you know, we've all too much kind of forgotten about, and it's an incredibly important one, and especially with respect to the lives that are in these buildings, and it's absolutely critical. So thank you very much, Susan, for doing this, and your firm, and the research and that your firm is doing. It's one of the firms that we've done work with, and thank you very much for this.
You're very welcome. Thank you for asking.
Brigitte, thank you for helping us, and obviously NFPA is on everyone's mind, and we look to it all the time, and it's nice to put a face to the organization, and thank you for your contribution to this, NORR.
Happy to be part of it, and thank you for bringing this important topic into your educational sphere here.
Yeah.
Thank you. And thanks, Kevin. And thank you to everyone that was on this session. And we'll see you in a month for our next one. Thank you all.
Thank you.
Thank you.
Bye-bye.